Alright, so let's continue on. This says, how many solutions do the following equations have? Justify your decisions by explaining why. So the how many isn't asking us to find what the solutions are. It just wants to know essentially this. There's three scenarios. We can have a quadratic that hits the x-axis twice to have two solutions. We could have one that hits it once for one solution. And we could have one that does not hit the x-axis at all, so it would have no solution. And the way to determine that is called the discriminant. And the discriminant was the part that was underneath the square root. So it's b squared minus 4ac. If your b squared minus 4ac is positive, you're going to have two solutions. If your b squared minus 4ac is equal to 0, then you will have one solution. And if your b squared minus 4ac is negative, you'd have no solution. And the reason for that is because it's the part that's underneath the square root. So if it's positive, it's two answers because of the plus or minus. 0 doesn't have a plus or minus because it's just 0 either way. And then if you're trying to square root a negative number, you can't, so there's no real solution. So before we do b squared minus 4ac, we do need to make sure that we get it all equal to 0 so that it's in standard form. And then we'll do b squared minus 4ac. And when we do that here, we'll get a 4, and then this is a negative 16 times a negative 2 plus 36. And so we get a positive answer. So 17 has two solutions. I'd have to do the entire quadratic formula to figure out what they are, but it does in fact have two solutions because it has a positive discriminant. Let's check this one out. We'll start off by getting it into standard form. And then we'll do our b squared minus 4ac. And we'll get a 9 minus, so we'll get an 8 times an 8, so 64. Here we'll get a negative answer. So this one, this quadratic, has no real solutions, which means we wouldn't even want to bother using the quadratic formula to finish finding the answers to this because there are no real solutions. And that's what the discriminant does, is it tells you if it's worthwhile to continue solving. It's not as important now because we have graphing calculators that can tell us what the picture looks like very quickly. But the discriminant used to play a large role because it would let people know if the quadratic was worth solving or not. So here we're going to go ahead and solve using the quadratic formula, which is our negative b plus or minus square root of b squared minus 4ac all over 2a. And as always, I recommend that you write out the template before you start to solve. Helps keep everything organized. Here for us, our a is 1. Our b, we need to subtract it to the other side to get it equal to 0. So our b is a negative 2. And our c is a negative 6. So you'll want to make sure you don't go too fast. So here would be negative 4 times a negative 6. It's positive. So here we'll get 2 plus or minus the square root of 28 all over 2. And that's our solution because 28 isn't a perfect square, and we're not able to take it any further. Now, I'm not able to do this. Do not try to simplify those 2's, because when you're doing division and you have an addition or subtraction sign in your numerator, you can't just cross off the 2's because that's leaving out the fact that the square root of 28 is also being divided by 2. So that would be our final answer right there. Let's try another one. So we'll write out our template first. And then what we'll do is we'll substitute in our values. So we get a 2 plus or minus a 4, and then we'll get a plus because we have a negative 4 times 1 to get a negative 4 times a negative 35, so that negative times negative turns positive, 140 all over 2, which means the part underneath the square root here is 144. Now 144 does have a square root, it's 12. So since there is a whole number answer there, we're going to want to switch off into the two different scenarios, which involves the plus or minus. So our two solutions for this one are 7 and negative 5, which means this original quadratic would have been factorable. If you would have looked at factoring it, it's the easy type, so it would have been f and f. And then you would have recognized, oh, I need numbers that multiply together to give me a negative 35 that also add to a negative 2. And then if you would have done the zero product property, you would have gotten that f is equal to 7. This is 0 here. And f is equal to negative 5, which is the same thing we got here. So I should really change these x's, because it wasn't our variable on this one, over 2f. The height h in feet of an object above the ground is given by this, right? Because remember that gravity is quadratics, where t is the time in seconds. When does the object reach its maximum height? So if we think about what that means, maximum height is the vertex. And we know that the vertex is negative b over 2a. That tells us the x-coordinate. And then we plug in the negative b over 2a into the original equation, and that will tell us the height. Because when you're looking at an axis, we'd have the time as the x and height as the y-axis. So we need the y-coordinate of our vertex. And so we'll actually need both, because A says when, so when is the time, is the x. And then what, that's the height. So all this is really asking us to do is find the vertex. So we need negative b over 2a. So we'll get a negative 64 over top of a negative 32. And we'll get that it takes 2 seconds to reach the total height, the maximum height. And then what is the maximum height? We're just going to need to plug in 2 into the original function. So we'll get negative 16 times 4 plus 128. So we'll get negative 64 plus 128 plus 190. And if I put all those together, we'll get a height. So our y coordinate of the vertex was 254. So the maximum height is 254 feet. It cost Acme Manufacturing $C per hour to operate its golf ball division. The cost is related to the number of golf balls produced per hour, x, and this relationship is described by the function, and then it gives us our function. Using the given function, what number of balls per hour should Acme produce to minimize the cost per hour of manufacturing these golf balls? So what's going on here is that we're going to have a curve that looks like this, to where we're looking for our vertex once again, but this time it's going to be a minimum, and they tell us that. But it's the same concept. It says, what number of balls should Acme produce to minimize the cost per hour? Well, the cost per hour is x, so we're looking for the y coordinate here. And to find the y coordinate of that vertex, we first need to do negative b over 2a. And so we'll input those here. And when we calculate this out, we'll get 100. So the 100 answers the question here because it says, what number of balls per hour? So I think I said a minute ago that we were looking for the y coordinate, but we're really looking for the x. So what number of balls per hour should Acme produce? 100 balls per hour. If we wanted to plug it back in to find the y coordinate, it would tell us what the operational cost is at that minimum point. Because if we were to graph this, the x-axis is the balls per hour, and the y-axis would be the cost. So here for 7, it says the width of a rectangle is 5 times its length. The area of the rectangle is 180 feet squared. Find the width of the rectangle. So what we'll want to do is set up the initial equation. So it says the width of a rectangle is 5 times its length. And we know that the area formula for the rectangle is length times width is equal to the area. So in this case is equal to 180. And it puts the width in respect to the length. So we have our length x, and it says that the width is 5 times that. So we'll have x times 5x is equal to 180. So we'll have 5x squared is equal to 180. And then we'll go ahead and start solving this out as an equation. So we'll divide both sides by 5. Get that x squared is equal to 36, and then we'll square root both sides. Now traditionally we've been talking about how whenever you square root in an equation context that you need the plus or minus symbol, but since we're talking about an actual rectangle here, we know that it can't have negative side length, so we're only going to talk about the positive 6 here. Solve by using square root method. This is going to be the same type of steps we just did in the rectangle problem, to where we're going to attempt to solve for our variable like any old equation. So the first step on this one is to add 288 to both sides. And then we'll divide by 2. And then when I square root both sides, we'll get that y is equal to plus or minus 12. This one, we add 25 to both sides and square root, and we get that x is equal to plus or minus 5. So these are just like solving regular old equations. On number 10, when we try to square root both sides, we can't square root the negative 4. So that's an example of no real solutions. So on this final section, it says solve using whichever method you prefer. You must use each method at least once. So let's talk about here when you can use each method. In order to use the square root method, your b value must be equal to 0. Go back up and look at 8 through 10. You'll notice that for all of these, they never had a b value. There were no regular x's. When you're completing the square, you need a equal to 1, and you need b to be even. so that when you do b divided by 2 squared, you have an even number to work with. Quadratic formula is when you can't factor it. If you can't factor it, or maybe it is factorable, you can't figure it out, quadratic formula you can always use. It's longer, but it's the most reliable. And then factoring can be done if you see that it's factorable. So if I had to choose, I would most likely only attempt factoring when a is equal to 1, making it the easy type. So let's look at 21. 21, I'll start off and decide, is it factorable? And then I'll recognize, yes, because I need numbers that multiply to 30, that add to a positive 7, and I would get those. And then I could use the zero product property. And we get that x is negative 10 and 3. And you could have used other methods on that. You could have used every other method except solving by square roots, and you would have got the same answer, but not as quickly. For 22, when you subtract the 8 over, and you try to factor this, it's not factorable. There are no numbers that multiply to negative 8 that add to negative 5. And it's also not a good candidate for completing the square because that 5 as the b value is odd. So this would be a good opportunity for to use the quadratic formula. And this is why we have different methods, because different scenarios will come up and you need to be equipped for them. And so on this one, we'll get this as our answer. And we can't take it any further because it's not a perfect square underneath the square root. So for this one here, it's also not factorable, but it's said up top that we need to use each method once, or at least once. So this is going to be the one that I choose to do completing the square on. So I'll get the c value out of the way, and then I'm going to do my b divided by 2 squared. So 8 divided by 2 is 4. And then when I square it, I get a 16. So I'll add a 16 here, and I'll add a 16 here. That allows it to factor to x plus 4, which is x plus 4 squared. We'll square root both sides and get that x plus 4 is equal to plus or minus square root of 12. And then when I subtract 4 from both sides, we'll get this. For 24, we'll want to make sure that it's set up equal to 0 first. This one is factorable from a GCF standpoint. And then we can use the zero product property to set up our pieces. This one here is a candidate for square root method because there's no b value, there's no regular x's in the way, stopping us from solving it in the traditional path. And then finally for this one, you could attempt to factor it. You could also use the quadratic formula. And so if you're attempting to factor it, you might check for some of the factors for some time, or maybe you recognize that you're not super strong at factoring when our a isn't 1, so maybe you go ahead and jump right into the quadratic formula. And when you do that, here's the setup. So we have this, and then as soon as you recognize that that square root of 4 is a whole number, What that tells us is that we could have factored, and we'll go back and take a look and see what that means, because here's us splitting off into the positive and negative case. We get the answers of 5 over 3 and 1. If you had factored this, you'd get the same answers. It would have been 3x and x. That's the only way to start. And then you're looking for numbers that multiply to a positive 5, that add to a negative 8 after they're multiplied with the O and I of FOIL. And what it ends up being here is the minus 1 here and the minus 5 here. Because 3x times negative 1 is a negative 3x. Negative 5 times x is a negative 5x, and those do in fact combine together to give us the negative 8x. And then if you would have used the zero product property and solved, you would have gotten the exact same answers that we got from the quadratic formula.